Yeah.
Did you say this was for?
Say it again.
You said the bisection method. What is this for? Like, is this for like the giving up or?
Oh no, so giving up is then all the methods. All methods you'll search, and some point of time you'll say, I've tried hard enough, I'm going to give up. Okay. So first bisection method. So first, as I said, we have three things: initialization, search direction, and termination. So let's look at all those things. Just put one here. Now this one requires two initial values. Okay, and they need to be specially chosen. What I mean by specially chosen, they have to satisfy these. So let's say that the initial values are x1 and x2. Okay, these have to satisfy f of x1 times f of x2 is less than 0. Okay, so why f of x1 times f of x2 less than 0? Let's look at a plot of some curve f of x as a function of x. Okay. So note that anything above this is a 0 line. Anything above this, f of x is positive. Anything below this, f of x is negative. Okay, so what does f of x1? Let's just choose one value here, x1. And this is the corresponding value, f of x1. We see that f of x1 is positive. Okay, so for this condition to be met, f of x2 has to be negative, right? So it has to be chosen in such a way that it is on the other side. Positive, negative. So when you multiply this positive value for f of x1 with the negative value for f of x2, which is right here, you get negative. So what is happening is just by the choice of f of x1 and x2, you sort of bracket the root. Now you know that at some point it's going to cross the x-axis, because one root is on one side of the on one side you have f of x is positive, one side it's negative. It better be that the root lies in between. Okay, so that's called bracketing. This condition is known as well, it's called the bracketing the root. Okay, so that's once you've initialized, the second step is the search direction. Let's try this font. Okay, so what we'll do is once we have x1, x2, we'll choose x3 as x1 plus x2 divided by 2. Okay, this is basically by the method as its name, bisection. Your search direction, you are bisecting, you're finding the midpoint of the 2 points. Now then we'll do two checks. We'll check f of x3 times f of x1, and we'll check f of, well, we'll just check we don't need to check both. We'll just check one of them. Let's say that f of x3 times f of x1 is less than 0. What that means is we basically chose this point x3 to be here. And if you take the product of f of x1 and f of x3, you're still bracketing the root. Okay, so in this case, what you'll do is you will essentially God, I lost my pen. Oh, it's here. Okay. Okay, if this is the case, then what you'll do is x1 and x3 is bracketing the root, and you no longer need x2, right? Because x1 and x3 is bracketing the root. So you'll replace x. Let me just change this. So then what you'll do is you'll take x3, you'll replace x2 with x3, because now once you replace that, now x1 and your new x2 are bracketing the root. So this becomes the new x2. So now again, x1 and x2, which is this point, are bracketing the root. Okay, if you find that f of x3 times f of x2 is less than 0, so okay, which means that now it will be on the other side, then you will replace x1 with x3. Okay, one of them will always be true, right? Either this is true or this will be true, just by the nature of how the curve looks. And then you'll repeat the process of computing f of x1, f of x2, seeing the sign, and just keep doing that. So this will be clear when I actually solve a problem. So let me actually let me write it this way. That way you can actually follow my notes and do the problem. So if this is true, then what you'll do is put x2 equals x3. If this is true, then you'll do that. Else, you clearly know that the other identity is true. So you'll f of x1 will be replaced with x3. And then you just keep doing number 2. The step 2 just keeps going till you reach a point where f of x 3 or f of x2, whichever you have, is greater than the termination criteria which you determine. I think it's just best for me to try to solve an example. We'll do an example by hand, and that'll make it very clear. And then I'll give you code which will do the same thing, which is generate that solution for you automatically by just doing these calculations. Okay, so here is a problem to illustrate the bisection method. So problem 1, use bisection method to compute the roots or the root of equation f of x equals x squared minus 3x. Okay, now I intentionally gave you an easy example, something which we can easily find the solution. So the solution for that is what are the roots?
0 and squared 3.
No, 0 and 3. Yeah. 0 and 3. So if you put 0, you get 0, f of x is 0. If you put 3, you get 3 squared minus, which is 9 minus 9 is 0. So we know 0 and 3. But just a simple example so you'll understand how this works. Okay. I'm going to give you the initial values. use initial value of 1, 4 and terminate when accuracy is 1e -3 or 10 raised to -3, the same thing. So once you are agreeing in the third decimal place, you should just stop.
I should take 6 or 7. By second.
No, actually it takes 20. It's not very fast. That's what I got from doing it, clearly not by hand, by doing putting it in octave. It's not the fastest method. There are better methods. Okay, so I'm just going to show you the process. Okay, something I want you to know is these things are probably very easily done in a calculator, or well, not calculator, but a code. You write a code and just put anything and it just spits out the answers. But a necessary evil of this class is that I have to test you in an exam. So you will be expected to do these calculations by hand in the exam. Now, for the exam, I'm not going to tell you to do 20 iterations. That just doesn't make any sense. I'll probably tell you, do 3 iterations or 5 iterations, just so that I know that you can do the calculations. But for 20 or 40 or 100 iterations, you have a computer. You don't have to do it by hand. So remember that. Be mindful that you have to do these calculations by hand in the exam. Okay. We have to do that so that I can test you. Okay, so here's what we'll do. The initial value is given to us. So we are done, knocked off with step 1. The step 2 is the search direction, and that's what the focus is really of this particular problem. So let's do iteration 1. Okay, so we know that x1 I chose as 1. x2 is 4, that's given to us. I need to compute f of x1. So just put 1 in this equation, you get what? -2. And put x2 in this equation, you get 8 -4, I think. The 4. Okay, so one, 4. Okay, I can draw this just because I know how the curve looks like, but normally I cannot draw it. It's something like this. It's 4 clearly. This is probably -2. Okay, so now that we did that, let's compute x3. That's 4 plus 1 divided by 2 is 2.5. Let's compute f of x3, which is f of 2.5. That comes to -1.25. We can actually see it here. This is 1. That'll be 2.5. So it's somewhere over here. We see it's still negative here, -1.25. Okay, which means that x1, x2. So then we check if f of x1 times f of x3 is less than 0. Okay, so that's basically saying is -2 times -1.25, but that's greater than 0, not less than 0, right? Which means that you need to replace x1 with x3. x1 equals x3 equals 2.5. So now This is the new x1, and now x1 and x2 bracket the root. So that's completes iteration 1. We go to iteration 2. Okay, now our x1 is 2.5. F of x1, we've already computed that. It's 1.25, negative 1.25. x2 is 4. F of x2 is, we've computed that to its 4. Okay, so then we ask the question, is f of, well, we need to do the third x3. x3 is x1 plus x2 divided by 2. So that's 4 plus 2.5 divided by 2. That comes out to be 3.25. F of x3 so f of 3.25 is 0.8125. Okay, so now we do the same thing. F of x1 times f of x3. So f of x1 is here, f of x3 is right here. So you can see a negative number times a positive number. Is less than 0, which means that x1 and x3 does bracket the root, and we need to replace x2 with x3. So x1 remains. I need to swap x2 with the new x3. So we've gone from 1 bracketed between 1 and 4 to bracket between 2.5 and 3.25. Yeah.
What is the number that the bracket reduces by each time you do an initiative? That's 25%?
I think it's 25%, right? Yeah, it's 25%, which is actually slow. The Newton-Raphson goes by the log or something, so it's 10 times faster. Okay, I'll do one more iteration and then I'll just surrender it to a computer program, right? So let's do iteration. X1 remains as 2.5. F of x1 is something we've already computed. It is minus 1.25. X2, we computed that using the bisection method, 3.25. F of x2, we've also computed in the past, so it's 0.8125. Using these two values, we can compute a new guess. X3 equals x1 plus x2 divided by 2. So it's 2.5 plus 3.25 divided by 2. That's 2.875. Okay. If you compute f of x3, that is, put that in x squared minus 3x, you get minus 3.59 minus 0.359. And now we can see if you do f of x1 times f of x3, f of x1 is negative 1.25, f of x3 is minus 359, is greater than 0, which means that x1, x3 is no longer bracketing the root because both of them have the negative sign. So we need to swap x1 with x2. Sorry, my bad. X1 with x3. Which is 2.875. So for the iteration 4, we're going to start off with 2.875 and 3.25. So you see where the brackets are shrinking as a result of this method. Eventually, you will see that it actually terminates. It gives you the value you want. So I'm going to show you code which can do this. I don't want to go beyond. I think I'll ask you for 3 or 5, up to 5 iterations in the exam, not more than that. Okay, so this function main root finding actually is written in such a way that I can get the answer for some equation I wrote down here. Oh, I wrote a different equation. I see x. Okay, we can change that. X square minus 3 times x. Don't have to worry about the second part. We don't need df dx. X square minus 3x. First. Okay, so approximate root is maybe hold on, let me just check I initialize it correctly, because it was a different. So I should, A is my lower guess, B is my upper guess, 1 and 4. And then I want to stick to a tolerance of 1e negative 3. And let me just say I'm going to stop at 100 iterations. So let's run this. Okay, so it was actually 11 iterations, not 20, as I said earlier. Okay, now it's better. Actually, I do a step. I also make a plot of this function. I've done this with 0 is one root, 3 is another root. We don't need that. Okay, so this is saying that the approximate root is 3.00024. Okay, remember I said it needs to be accurate to 3 decimal places. So I actually stopped when the 3 decimal places were equal to the root, and that is the 3 significant places were accurate, and then stopped. And then it took 11 iterations. Okay, let's look at the code which does bisection. This function basically just provides it with bisection method. I need to pass the function, the bracketed roots a and b, the tolerance. This tolerance is when I want it to terminate, and the maximum iterations. Now, there is something about this function f which I think I've not taught in the past. An easy way of writing functions in Octave or MATLAB is to use anonymous functions. Okay, so instead of writing my function and separate file for it, you could actually write it inline like this. I think it's self-explanatory. F is the function, x is the input argument, and the equation is x square minus 3x. You really don't need this, this, right? Dot. It basically allows you to multiply an array with another array. So if x was an array, then you can actually multiply element-wise using that. The only reason I put this dot here was because I was trying to get a plot. But if I don't have a plot, I don't really need it. Okay. So this is the function. It is passed to bisection method. Bisection method here has f, x1, x2, tolerance, max, etc. I hope it is self-explanatory if you look at the notes. So I need to check the sign of the multiplication, sign of f of x1, sign of f of x2 greater than 0. Well, technically, you don't need to put sign. You can just do f of x1, f of x2 is greater or less than 0, but I just use the sign. Doesn't really change the logic is the same. Each time you update the search direction, x3 is x1 plus x2 divided by 2. You compute the new f of x, which is f of x3. You basically, depending on the sign, you change depending on that sign, the multiplication less than 0, greater than 0, you substitute the bracketing component of it. So you replace x1 or x2 with x3 depending on which of those two values brackets the root still. And then this is actually checking if it's within the tolerance. If it's in the tolerance, you just exit. Here, the tolerance is slightly different, actually, on how accurate x2 is. If x2 doesn't change much, then the root, then it basically terminates. But you could also have a condition which terminates based on f of x3 or f of x1. Okay, and then there is some other things like max iterations reached. So if you now took this code and you said, you gave initial guess, of, let's say, you still need to bracket the root. So if you have, so I had 1 and 4, right? 1 gives a negative. So let me just put 100 instead of 4. So 1, 4 was kind of close. Can you guess how many iterations it will take? It's actually pretty fast, I think. It will be close to 11, I think. It's 14, just 14 iterations. And print the root. Yeah, 3.00061, 14 iterations. It's not too bad. Now, the good thing about the method is that you need to, it usually converges if you can bracket the root. Okay. There could be one issue though. Can you guess what could be an issue with this method, with the bracketing component of the method? You started with 1 and 4. Remember, 2.5 was the first one. Minus 2. Yeah, this is how I would like you to present the solution. So this one for 3 decimal places converges in about 12 iterations. So you can see f of x3 is 0.0007. That's when you stop. Before that was minus 0.0015. Look at f of x3 at iteration number 11. See, it's minus 0.0015. So that was accurate to, that was not 0 in the 3rd decimal place. And so then next one I stopped. Okay, so this is how I want you to present the solution. I'll put this in the notes when I post the notes. Same as bisection. So nothing more to be done. You just need to bracket the root. The second step, the search direction, however, is different. Okay, this is what is done in the regular-Falsi method. The curve, remember, we have to bracket the root in order to use this method. So let's say this is f of x1, this is x1, this is x2. Okay, so what is done is, instead of using x1 plus x2 divided by 3 to choose the initial guess, you actually draw a line between f of x1 and f of x2. So if you draw a line, then this will intersect the x-axis at some point. Let's call that x3. Okay, and that x3 is your new guess. This is a new guess. So what that is really doing is it's saying that I'm going to approximate this curve from f of x1 to f of x2 with a straight line. Okay, and then use that point where this line intersects the x-axis to be my new guess. Now, if our assumption that it was a straight line was true, then that would be the solution, right? But if it is not, it's going to be off like it is here. And then you can redo the calculation. So we need to do a little bit of calculations here to figure out what this x3 is, because we need to draw a straight line. So we know that the straight line passes through 3 points here. One of them is x1, f of x1. It passes through x2, f of x2. And then we know that this point is x3, and the y coordinate is 0, right? Just by construction. So if you want to write the equation of a straight line, it would be, just take the ratio, right? F of x2 minus f of x1 divided by x2 minus x1 equals f of x1. I'm going to take x1 and this x3 here, x1 minus x3. Okay, now we can solve for x3. Okay, so there is a little bit of math which I will not go through. You don't need to do that yourself. Just trust me on the final answer. This is what you'll get. Okay, so this is the update compared to bisection, which was just x1 plus x2 divided by 2. It is a little bit more complicated. The good thing about this is that it actually uses information from f of x to update, while the bisection method did not use f of x for the update. It was just the arithmetic mean of x1, x2. And then once you do that, the part on updating the search direction is the same. You use the sign of the product to figure that out. Let me quickly show you how this works for numerically for using the code, and then we'll stop there, which I'll open. Okay, the only difference between bisection and this one is that it uses this update rule, which I just wrote down. That's all. Okay, now what remains for us to do is to actually explore how these solutions compare. So I have uncommented regular-falsi, and I have uncommented bisection. So it'll run both of them. And maybe I can just comment out the part where it draws the plot.
Professor, what do you press to comment everything?
Control plus R and Control Shift R to uncomment. You can actually find it here if you highlight, right click, format. It says here comment. Okay, so let's just start with the initial guess 1 and 4. Okay, so we have 3.00 bisection, 2.999, 11 and 12 iterations. Okay, let's try 100. Okay, 99 iterations. Wow. Try put. Oh, B, that's fine. I'm just trying to compare the two. 13 versus 99. Yeah. Just seems like it just shouldn't be 99 iterations. Let's try the other way, which is minus 4 and 1. Now here, regular-falsi beats bisection. And try. Okay, here is a case where called from. There's a warning. I need to figure out what the warning is, but does that bracket the root? It does, right? 0 and yeah, it does bracket the root. Okay, I have to check. It's a little too far, but yeah. So that's how you'll use the code to explore. And as I said, you want to put that table.